Welcome to Lecture 5, Linear Momentum and Collisions. It's early in the morning right now, so this lecture comes with extra bass. Chapter 9, Linear Momentum and Collisions. Linear momentum, p, of a particle of mass m moving with a velocity v is p equals mv. Linear momentum's conserved, so that means that if you have a system where no external force acts on it, then the momentum before some kind of an interaction is equal to the momentum after that interaction. A system can't change momentum unless an external force acts on it. The impulse momentum theorem says that the impulse is equal to the time integral of the force, and that the impulse is also equal to the change in momentum. So if a force acts on a system over some kind of really short time scale, say, and you don't know exactly what the force is, you could use this equation to calculate what the average force must have been if you know the interaction time. This is useful for collisions and trying to figure out how much force is on this combination. If we know that they're in contact for maybe 5 milliseconds and we can figure out the total momentum change, then we could figure out the average force and use that as a way to say, well, what do we think? Is this particle going to break from this force given how much force we know it can take? Elasticity of collisions. If two particles collide, then we can distinguish between different kinds of collisions. An elastic collision is one where the kinetic energy is conserved. Inelastic would be one where kinetic energy is not conserved. A perfectly inelastic collision means that not only is the energy not conserved, but the objects actually stick together after the collision. Center of mass. Position vector of the center of mass of a system of particles is the mass average of the position. So it's a weighted average of position weighted by mass. And then you just divide that by the mass afterwards to finish off the weighted average. So you add up for all the little particles, their mass times their position. This is a vector position. And then divide the result by the mass. Now, if it's a distributed object, it's not like a collection of point masses, then you really have to turn this into an integral. Similarly, velocity of the center of mass would be the sum of the velocities weighted by the mass of each piece divided by the total mass. And the momentum of the system is the top part of this if we just don't divide by the total mass. Newton's second law applied to a system of particles. The net force we know is m times the acceleration of the center of mass, which is also the rate of change of momentum as long as the mass is not changing. Two questions, or rather some questions now. Two astronauts, both 70 kilograms, are floating motionless in space far from Earth. One holds a 20 kilogram oxygen tank. He then pushes this tank directly towards a second astronaut who catches and holds it. If the speed of the tank relative to the second astronaut was 2 meters a second, find the final speed of the second astronaut relative to the first one. This is just a momentum conservation question. So, the throw conserves momentum. It's kind of like two different collisions. The first one is a separation, but you still treat it like a momentum conservation thing because it's happening internally. So we've got velocity of the tank, we've got velocity of the first astronaut. This is a one-dimensional problem, so we'll just use one-dimensional vectors where we have positive and negative velocity to indicate like a right and left direction maybe. So I'm imagining that the astronaut throws the tank to the left. That means that VT will be negative 2 meters a second. If you had VT as positive 2 meters a second, that's okay too. You're just imagining the tank being thrown to the right. As the second astronaut catches the tank, then here the mass changes. So we've got the mass times velocity of the tank plus big M, the astronaut mass, times velocity of that second astronaut originally, which was 0. So that's why the left-hand side is just mvt. And that's equal to the new combined mass of the astronaut and tank times the new velocity of that astronaut. So we're asked to find the difference in velocity, v2 minus v1. Substituting in what we found, we can work out this equation, 2 times the astronaut mass plus tank mass over astronaut mass times the sum of the astronaut and tank mass times the tank mass velocity of the tank. Okay, that's an equation right there. Let's see if we can find some limiting conditions on this. Whenever you come up with an equation like this, you know that it's a good idea to say, all right, well, let's see if we can move some numbers around and check if the answer changes the way that we would expect. So what would you expect if the astronauts had a much larger mass than the tank? Well, you'd expect that the velocity would not, that they wouldn't get very much of a velocity change by throwing this tank from one to the other. Sure enough, if m is much bigger than little m, we can cancel out this numerator and denominator factor and come up with just this, which says a couple of things. So the first part is that we can ignore the change in the second astronaut's mass as he catches the tank and then just say we're transferring a momentum of the tank momentum from one astronaut to the other. So the first astronaut loses that momentum. In other words, he gains it in the opposite direction, and the second astronaut gains it in the direction the tank was going, which is why the momentum change between the two of them, or the momentum difference that they pick up in this process, is 2 times what the tank momentum was. And in a further limiting case, as you can see, if m goes to 0, then so does the velocity change. Let's look at some other cases. So what if the tank mass is much bigger than the astronaut mass? Coming back up to our equation now, in this case, it limits to a similar form of equation to if the tank is much less massive, except we lose the factor of 2. So now what happens is at the opposite end of it, the astronaut's mass is neglected relative to the tank's mass. And so the tank kind of just keeps moving along with that velocity that it had, the velocity of the tank. That's why that changes. But then you may be sort of surprised, okay, if the tank was much more massive, why do we see this divided by astronaut mass here? And that's because in order to, the relative velocity is dominated by the first astronaut's velocity. So what happened here is, in order to give the tank that momentum, the first astronaut must have flown off in a really fast, at a really fast velocity, because his mass is negligible compared to the tank's. So this is entirely a velocity change from the first astronaut in the limit. And the final situation where the mass is equal to the mass of the tank, so the astronaut mass is the same as the mass of the tank. Now, this equation says that we've got 3/2 VT. This one you can kind of picture as well. So the first astronaut pushes off with VT in the opposite direction, and the second catches the tank. Then she starts moving with velocity V of the tank over 2. Next question, what's the rate of change of linear momentum? We mentioned this briefly, do you remember? Rate of change of linear momentum is the force. Here's the derivation of that. A cannon on a cart fires a cannonball. The momentum of the cart cannonball cannon system is conserved in A, the horizontal direction, B, the vertical direction, C, the horizontal and vertical, and D, neither the horizontal nor the vertical. Think about the forces acting on it. The forces in the horizontal direction would be there's no external force in the horizontal direction. So that means the momentum has to be conserved there, because we're considering the cannonball as part of the system. So if we were to just look at the cart and cannon system, its momentum would not be conserved. The cannonball leaves in this direction, and that puts some kind of a, while it's doing that, there's a force on the cart in the left direction, and so momentum would not be conserved there. What about the vertical direction? As the cannonball is firing, it puts a force downward on the cart, and kind of flies off in this direction. While that's happening, the cart is acted on by the normal force. So if there was no ground, picture there being no ground, then the cart would fly off in the opposite direction, right? But it doesn't do that because the ground is there. So even if there were no, imagine there's no normal force, no gravity, the cart would fly the opposite direction. But because it doesn't do that, that means there must be an extra net force on it in the, or an extra force on it from the ground. So basically, the ground prevents the vertical motion that the cart would have to do to conserve momentum in the cart cannonball system by putting an extra force on it. So the ground prevents it with the normal force. As the cart tries to move through the ground, the normal force says no, and it stops the cart. That's an external force acting on the system that's unbalanced by gravity. So a net external force acting on the system, and therefore the momentum is not conserved in the vertical direction. Tarzan and Jane. Tarzan, mass m, big M, swings from a tree using an r equals 4.5 meter, initially horizontal rope tied to a tree branch here. At the bottom of the swing, stationary Jane, mass m equals Tarzan's mass over 2, grabs onto Tarzan and swings with him. What is the max height the two will swing to? Okay, so what you do is use energy conservation from the top to the bottom, figure out what Tarzan's velocity would be at the bottom, then inelastic collision with Jane, and the two conserve momentum. You can find out the new velocity, new kinetic energy, and then find the maximum height that they get to from there. Let's go ahead and do that. Downswing conserves energy, so we've got the velocity at the bottom. Collision's inelastic, final velocity related to the initial. Upswing conserves energy, so the final velocity kinetic energy at the bottom gives you the gravitational potential energy when they reach height h at the end, and you can solve for h. Substituting in, you find that the h ultimately depends only on the ratio of masses and the initial height. So we come up with some limiting conditions here. If Tarzan's mass is much larger than Jane's, then this limits to 1, and so we just have the final height is the initial height. That makes sense. What if Tarzan's mass is much smaller than Jane's? Then there's basically the momentum transfer leaves us with no velocity and no energy left, and so the final height is 0. They just stick at the bottom. If the masses are equal, the new height will be r over 4. And if the masses are such that Tarzan weighs twice as much as Jane does, as given in the example, we've come to a final height of 4/9 r. Okay, for this question, I made up a new intellectual property kind of character. So this is about the adventures of Springzan. Springzan's like Tarzan, but he's covered with springs. You can I did a Google search and nobody's made a comic book about this yet, so there may be some marketing opportunities there. Anyway, Springzan, mass m, swings from a tree using an r equals 4.5 meter initially horizontal rope tied to a tree branch, just like the last problem, except at the bottom of the swing, Springzan is covered with springs, so elastically collides with Jane, doesn't pick up Jane. Determine the velocity of each after the collision. All right, so this is an elastic collision, which means momentum and energy are conserved. This time we're going to go and solve the system of two equations using Maple. So here's some code that you can use to do that. The notation of Maple's a little bit finicky with its syntax. It needs the list of equations to be in curly brackets, but then it wants the variables that you want to solve for in square brackets. Maple gives us two solutions here too. So this is a case where we have to combine what we know about the problem with what the computer says. The first solution says, well then the final velocity of Springzan is just his initial velocity, and Jane's final velocity is 0. That would conserve momentum and energy. Yes, that's true, but that's the case where Springzan just misses Jane, and that's not the one we're looking at. We're looking for the one where Springzan collides with Jane elastically, and that's this solution here. Okay, so looking at our limiting cases as usual, if Jane's mass is much larger than Springzan's, then Springzan ends up moving in the opposite direction. So, or actually not even much larger, just larger at all, then Springzan moves in the opposite direction. If Jane's mass was equal to Springzan's, then this is the case where this velocity is 0, so Springzan just stops moving at the bottom, and Jane flies off with Springzan's initial velocity. It's a maximum energy transfer. So all of the energy that Springzan has gone into Jane in this case. What if Jane's mass is much less than Springzan? This is a bit of a surprising case. So Springzan keeps moving basically the same as what he was. He ends up with almost the same velocity as before, but a little bit of energy does get transferred, and Jane ends up flying off with 2 times Springzan's velocity. So if you have, say, a bowling ball swinging down and it hits a ping pong ball, if it perfectly elastically collides, the ping pong ball flies off with double the bowling ball's impact velocity. For the numbers that were actually given, where Jane weighs half of what Springzan does, we come up with a final velocity of Springzan of 1/3 of what it was before the collision, and Jane's velocity is 4/3.